That was awesome. Thanks for talking about some old ice. We're gonna fast forward 2-ish million years and just talk about the last 100 years or so. So my name's Gabriel, with or without the dress last night, and I'm at Dartmouth College in New Hampshire, thanks to the funders. So this is a picture of one of our field sites in Greenland. You can see the little tent that we stay in the foreground, and in the back is the 12-foot by 12-foot like kitchen tent in the middle of the ice sheet with no rocks or animals or plants or people or anything. So 5 people for 12 weeks. It's a lot. So thanks to Daddy Dartmouth for funding this work. So if we look at the major ice sheets in the world today, Greenland and Antarctica, a bunch of previous studies have shown that Greenland is losing mass a lot faster than Antarctica. So here is the mass balance in gigatons of ice per year, so billions of tons, that is being lost from the ice sheets. It's around 300 gigatons per year, is equivalent to 1 millimeter of sea level rise per year. So Greenland, highlighted here, is losing a lot more mass than Antarctica. And if we model this forward throughout the rest of the century, we're looking at 1/2 to 3/4 of a meter of sea level rise, distributed differently around the world, but still large implications for how much mass is being lost off of this ice sheet. So if we think about a typical ice sheet, we can break it up into different zones, and above the equilibrium line altitude, it snows more than it melts on average over the course of a year. So we're standing on snow, not on solid ice. And if we think about what is coming in and out of this boxed system, it's just snow and rain coming in, and it's just a little bit of melt that's percolating down, and then whatever is evaporating or sublimating off. So it leads to pretty simple math to think about how healthy is this glacier. If it's snowing a lot more than it's melting, the glacier is doing good. If it's melting more than it's snowing, the glacier is losing mass into the ocean. So we can break the Greenland ice sheet up into 6 major drainage basins and compare how well regional climate models, which are these bars, estimate the total mass balance of each basin. And you can see in the northeast, in Basin B, 2 of these climate models differ by about a factor of 2. So very large differences in some regions, versus on the west coast in Basin E, they agree plus or minus 10%. So that's doing pretty well for these really complicated regional climate models. But how can we have any faith in these models if in some regions they differ by a factor of 2, and in other regions they differ by 10%? So we, by we I mean not me, wrote a grant to go snowmobile across, where am I pointing this? Here we go. Across the western percolation zone, mostly in Basin E, a little bit up in F, over 2 seasons, to try and validate these climate models and say, are they doing a good job? How well and where do they need to concentrate their efforts? So if you've never had the benefit of snowmobiling across Greenland, it looks like this. You're going about 6 miles an hour for 10 hours a day for 12 weeks. And that's what it looks like. So you try not to fall asleep as you're literally sitting on the snowmobile, and we all fall asleep, and you fall off, and then everyone laughs, and you get run back to the snowmobile. So as we're driving along, we're hauling all of our gear, so all of our science stuff, technical term, all of our camping gear. It's like -20 to -40 Fahrenheit, which is cold in Celsius and in Kelvin. Huge Canada Goose parka jackets and huge sleeping bags and a lot of food just to feed 5 people for 12 weeks out there, and like emergency gear because the US requires all of this stuff. And we're out there to do science. So on the top you can see maybe me, maybe Thomas, snowmobiling, dragging a blue sled of gear as well as a GPS, and in the little orange sled in the back there is a radar antenna. So we're not electrical engineers, but you imagine an antenna, it sends out a ping, downwards mostly, and it bounces off of different layers in the snow, and then the electromagnetic signal bounces back to the antenna. And based on how strong that echolocation is, you can see different stuff in the ice. So here's an example of one of these radargrams with distance along a traverse on the x-axis, and the time of how long you're listening on the y-axis in nanoseconds. And if you tilt your head, you can convince yourself you can see some internal layers within this radargram, but we don't know how deep we're looking or how back in time we're looking. So as we're there, we drill some ice cores, which are these vertical red bars, at a couple of the different camps that we stopped at. So as every good grad student does, you watch your advisor do the work for you. So here's my boss drilling one of these ice cores. We're only going down about 30 to 40 meters. Last talk, you were going down like 100 to 200 meters. So most of what we're doing is manual or backbreaking. So you drill down and you pull up, if you're lucky, about a meter of ice at a time. So this was the best run that we ever had. It's about 120 centimeters of ice, and you drill down 1 meter at a time, so it gets progressively slower throughout the day. But you get something like this and you're really happy. So we can measure the length and the diameter of each section of ice, mostly 20 centimeters or 30 centimeters, and they always break as you're trying to pull them up. So we can measure the mass as well, and then easily just calculate the density. It's approximately a cylinder, plus or minus. So we can plot out the depth versus the density of one of these ice cores. Andrew had a great poster last night of how good of a job do the models do. And it depends where you are, but here you can see one of the models in blue versus our actual measurements in reddish orange. So you can see in this area, it's pretty warm, so it's melting a lot. During the summer, in the top 10 meters, it didn't used to melt a lot in the summer, as you can see down lower. So the models somehow need to be updated to account for this melting that's happening. So once we have a good estimate of the density, we can calculate how quickly the electromagnetic speed from this radar propagates down through. This is the scariest math you see, multiplication. And once we know the velocity, we can just get the depth from that. So we take these ice cores, we put them in a big Ziploc bag, we put them in a box, we put them on a cell onto a plane, onto a truck, and we get them back to Dartmouth, and we can melt these ice cores. So here's 7 of our ice cores, down to about the top 30 meters, and a couple older ice cores we're using to estimate the depth. We take these ice cores back at Dartmouth, and we can analyze them, so we can melt them very slowly and cleanly and controlled through some chemistry system. So you can see here's some oxygen isotopes, some major ions, and then how dusty it is. And this is just the top 10 meters of one of our cores. We know when we were there drilling it, so we can count backwards in time, like rings in a tree. We know that some of these isotopes have minimums in the winter, and some other chemical proxies we can use to date them. So we count backwards, we can count backwards starting at when we drilled it and get a really accurate depth age scale for each of these ice cores. Then we can calculate accumulation, so how much it snows very accurately with sub-annual resolution at each of the ice cores, back about 50 or 60 years, depending on where we are. So going back to the same radargram, now we have actual depth instead of just time on the y-axis, and we have dates at each of these cores. So we can do pretty much a PhD version of connect the dots. So this is 1981, and this is 1981, and that is 1981. We can connect these internal reflection horizons across. So Ben had a great poster on a bunch of layers last night, looking much deeper to calculate temperature. We're just going down the top 30 meters. We can trace these out, these internal reflection horizons that have been shown to occur at the same time everywhere as you trace them out. So if you think of 2 adjacent green lines, these horizons, you can know the depth between each 2, and you can know the time difference between each 2, and now we have a good estimate of the density. So you can calculate how much it snows anywhere along here, just dividing the time and the distance between them with the density. Everyone's favorite statistical error propagation through that. We don't have to go into it. And now we can get to some questions. So for instance, how much does it snow along the traverse? How does it change spatially? As well as we're looking back in time over the last 40 or 50 years. So how does that change over time? And then the models that are trying to answer these questions, how good of a job are they actually doing in this region? So here's a map showing kind of our whole traverse with starting here in 2016 up to Summit, and then a big clockwise loop in the second year. And it kind of looks like a Jackson Pollock painting where it stows somewhere between 0.2 and 0.6 meters a year, but we don't really know what that means. So we can look along a little transect from A to A prime and compare with some other papers. This is funky. Some other papers and some models. So our GPR accumulation shown in light blue here. And you can see some of the models do a great job. There's a yellow model hidden back here and a magenta one that agree really well over this domain, versus this one in green and the one up in black seem to over or underestimate along this traverse. So we can plot this out for our whole spatial traverse, and in red is where the models overestimate accumulation, averaged over the last 40 years, and in blue the models tend to underestimate accumulation. So in the intro, I gave kind of an average for each drainage basin, and on average, they do pretty well. They're within 20%, which is great for climate models. That's like actually really accurate. With the root mean squared, and if you just take the mean, where you're averaging out some high pluses and some high minuses, then you get errors of 3–6%. So that's great. It's not really accurate, but a lot of the papers will give you the mean difference. However, when we zoom in closely, you can see there's some areas, such as down in the southern region, where these models are overestimating by 30 or 40%. So that's averaged out by some blue underestimations, but these are some of the areas that these models should probably revisit and refocus on. We know Greenland's getting warmer. A lot of people have said that. So here's a temperature measurement from Kangaroo Loosewhack. And as we saw in the atmospheric session yesterday, warmer temperatures should hold more moisture, should lead to more snow. Just warmer air can hold more. So we would expect more snow with these rising temperatures, which is kind of the opposite of what we're seeing. So we're seeing that it's getting drier from ice cores, from GPR, and from weather stations over most of this western area of Greenland. In addition to not snowing as much, we're seeing that it's melting a lot more. So just looking at what percent of our snow is remelted in these cores, we can see increases in trends for almost all 16 of our cores. So in summary, we can calculate how much it's snowing over this 4,000 kilometer traverse. We can say how good of a job the models do in some places and in some times. And we see that it's snowing a bit less, and that's not offset by how much more it's melting in this region. So I'll thank the crew with me in the field, my advisors, and I'll flip back to the conclusions if you guys have any questions. Thanks.
Can you speculate what the models are, what parameters they're either missing, or what parameters maybe the modelers don't have, the data they don't have access to, that they are over or underestimating these mass balances of these things?
Yeah, awesome question. They're doing a really good job, and they're using all of the available data that they have. So we revisited, I think, 8 ice core locations that were drilled in the late 1990s, which is the only other time that anyone's ever been here. And a lot of the models are using data from the 90s, which is all they have. And we see lots of changes since then. So I just think a lot of the validation that many regional and global climate models are using are outdated because it's expensive and hard to get to these areas.
Yeah, thank you. This was really interesting. So you looked at some temporal changes in air temperature. I'm wondering if there's enough layers in the radar data that you could look at temporal changes over the last 30 years or something like that in accumulation.
Yeah, so in one of those radarograms you could see 10 layers that I had picked. So you get 9 time periods of accumulation through that. And what I'm showing in this figure, there's the background of the model change in surface mass balance, and on our traverse I'm calculating a linear trend in accumulation from our radar data. So looking at all the radar data that we have, we have accumulation for each time period, and I'm saying, is it snowing more or snowing less from that radar? So that's exactly what I'm doing here. And pretty much everywhere in the radar, we see that it's snowing/raining less.
One more quick question, sorry.
So you said that the increase in melt is not offset by an increase in snowfall. Do you know when you start to see that divergence in the record, like when you start seeing this increased negative mass balance?
Yeah, that's like a really good intro slide that I often use and don't. But it's sometime in the mid-1990s that climate indices shifted. The AMO shifted from negative to positive, and you see a very large, like, step decrease in surface mass balance right around that time. Glaciers are very slow and sluggish to respond, but that's when we saw kind of a massive acceleration in mass loss of the Greenland ice sheet.
Between 98 and 02-ish?
Yeah, late 90s, yeah.
Okay, let's thank Dave.